right? Hello to everyone who watches in the recording. So today we will start the core part of the course. I mean, we start quite fast. We just finished 2-lecture recap of linear algebra, and we are pretty much ready to get into the, the meat and potatoes, if you will forgive me for metaphors, of the course. The idea is that we are aiming at understanding well convex optimization, and convex optimization has closer relations with linear algebra, but in some way you can think of it as a step forward. So, for example, linear algebra provides us completely with tools to solve least squares problem, whereas convex optimization can be seen as the next logical step, giving us quadratic programming. Of course, linear algebra can also be seen as a subset of convex optimization, at least the squares can be, etc. So we're not doing philosophy here. I'm not going to dwell on definitions too much. But what I aim today is to show you how we can solve something that cannot be solved with linear algebra. And that will be the first time when we have to come face to face with what convex optimization is and how it is different. Okay, good. Now let us just start with some very simple tasks. So problem one. Let us minimize norm of x. That is a problem. Find me a minimum of the function norm of x. Can someone tell me what is the solution to this is?
0.
Exactly. Exactly. You cannot find anything that would give you a smaller norm of x than x equal to 0. That doesn't depend on dimensions of x, right? X can be n-dimensional, scalar, anything. Good. What about problem 2? Minimize norm of ax. Minimize norm of ax. What about this one? What is the solution here?
Also 0.
0 is a solution, yes. But can someone provide me any other solutions in 0?
Null space of A.
Yeah, any vector that lies in the null space of A would also be a solution. We didn't ask to minimize the norm of x, right? So 0 would be the smallest solution to this problem, absolutely. But if we just want a solution, anything in the null space of A will suffice. By the way, what if A is full rank? What will then happen?
Then there will just 0 vector.
0 is still a solution, right?
Yeah.
So the null space will be what we call trivial. So it will contain only a single element, 0, x equal to 0. Okay, good. So still null space is still a solution. It just contains one element. Good. Now, problem 3, minimize ax plus b. Here I want to point out that we already saw this problem on the previous lecture. And but we saw it in this shape. We wanted to find the smallest possible difference between ax and b, because we were solving ax equal to b. We were solving this problem, right? Ax equal to b. Oops. This problem, right? And from that, we got into this minimization. And we know how to solve it. How do we solve it? Well, we solve it with pseudo-inverse. That is a solution to the least squared problem. We say x equal to a pseudo-inverse b. That is a solution to this problem. And since this is a solution to the problem ax minus b, minimize norm, then to get a plus sign here, we just make b absorb the minus sign, right? So this is the same as minimizing norm of ax minus minus b, right? Something like this. It is the same as minimizing this function. So those two are equivalent, right? And therefore, we know how to we know how to work with this one. With this one, we work by saying that it is equal to a pseudo-inverse times this component. So a pseudo-inverse, right? A pseudo-inverse times this component, and this component is minus b. So b goes here, and the minus goes here. Okay. So this is how we can think about it. We could have actually just solved the whole thing using least squares again, but at the end of the day, what we need to recognize here is that everything that is different from what we saw in the previous lecture is a minus sign, and we should be able to feel comfortable with those. It's just if it is a plus sign here, we have a minus a plus b. You don't have to memorize it. It is, all you need to memorize is that the solution to this guy is this guy. That is all you need to memorize. Everything else is clear. And this guy is this guy, right? So when the sign is different, you get a minus sign here. Okay, all right. So somehow this problem is also clear, and the solution is minus a pseudo-inverse b. And I do realize it is annoying that we have different signs, but so is life. So is life. Okay. Next, let us consider problem 4. Problem 4. Problem 4 is should be familiar in some ways. What we want to minimize is norm of x. So normally a solution would have been 0, right? As you said in the beginning. But there is one caveat. We want ax to be equal to c. So we cannot just take any x. We have to take x which solves this equality. In fact, this equality represents what we call a hyperplane. We didn't talk about it yet, but we will soon enough. So this is a hyperplane. What do I mean by a hyperplane? Well, if it was ax equal to 0, this would have represented a linear space, right? A linear space is just a span of vectors that goes linearly, kind of like a plane, but it goes through 0. That is important part of being a linear space. Like you can visualize it as some sort of a like space like this, but importantly, 0 is part of this space. That is a linear space, right? It includes 0. When we say hyperplane, we mean a linear space, but it doesn't have, but also all other kind of like collections of vectors, which don't necessarily include 0. So for example, if you have a 0 is here, let's say, and your hyperplane is somehow like parallel to it, that is a hyperplane. What do you mean by hyper and plane? Well, plane is because this planar, right? It's still linear. So this is a linear equation here. And that is why it represents a plane. That I give it to you that can be unclear on the first side, the fact that the linear equations represent planes, but you probably have seen pieces of this before, right? If you want, just think of any way you can describe a plane, you'll find that the equations are linear. Like just write down any equation that describes a plane, you'll find it as a linear equation. Okay, most likely, of course, maybe you'll find a way to do it non-linearly. I'm not sure, but school program gives you linear equations always. Now, okay, so fair enough. All right, that's why plane. Why hyper? hyper, it just means that it is not necessarily two-dimensional. Planes in school program, in high school, are two-dimensional objects in three-dimensional space. That's how we think about planes in the high school. But in general, planes can be m-dimensional bodies in n-dimensional space. So they can be, 5-dimensional planes in 10-dimensional spaces. Right. Can be anything. A line is one-dimensional plane, hyperplane, in a three-dimensional space, for example, right? Or it can be two-dimensional. It can be one-dimensional, hyperplane in two-dimensional space. But so we call it hyperplane just to indicate the linear object not passing through the origin, existing in some linear space. Okay. Why it doesn't pass through the origin? Because of C. Okay. I think we said enough about the geometry. If you have questions, stop me and we'll discuss more. But yeah, this is so this indicates a hyperplane. It indicates that X have to lie on some object, kind of like this, kind of like this one here, and it not necessarily 0 is not necessarily on that object, so may not contain 0. Good. So what do we do in this situation? Well, we just need to find element on this hyperplane, which would actually be the smallest by norm. How do we do it? Well, first step I would suggest is to find all solutions to this equation, so to the constraints. We call this thing constraints, okay? We call it constraints. It represents a hyperplane in this case, but in general, all those subject to kind of like statements, we call them constraints. Whereas this is what we call a cost function. This is a cost function, so what we want to minimize. And those are constraints, what we want to uphold. Okay, so cost function, constraints. And we want to find all solutions to this equation. So all possible X. Constraints tell us what X are possible, what X are not possible. So let us just find all X's which are possible. So all solutions to this equation. Not just one solution, all solutions. Let us find them. Right, good. All solutions can be written like this, where you have a particular solution here. So particular solution given is the smallest norm solution given as a by pseudo-inverse least squares problem. All right. And we have a null space solution here. Okay. So N is a null space of A, is a orthonormal basis in the null space of A. That is all material from the last lecture. So you can imagine this part in pink, that is a vector line in the row space of A. This part in green is a vector that vectors that lie in the null space of A. Okay, that is the space of all possible solutions to the equation. Now, this row space and null space vectors, they are orthogonal to each other. How do we know? Well, row space is orthogonal complement of the null space, material from the previous lecture again. So if one lies like this, another has to lie like this or like this, cannot be like, angle between the two vectors cannot be anything but 80 degrees. Okay, P over 2. So those two vectors are orthogonal. Okay. That means that adding, like the smallest solution, that means the small solution will be obtained when this guy here is equal to 0. Why? When this guy is equal to 0. Why should it be equal to 0? Well, because if it is bigger than 0, the X increases in size How do I know? Because those two components are orthogonal, and the Pythagorean theorem, or whatever way you would prefer to call it, tells us that if you have one vector plus another vector, right, and they are orthogonal, the sum of those two vectors would be bigger than each of the previous ones, right? In particular, it will be bigger. So if you imagine, for example, this as being null space component, and you imagine the other one to be, let's say, this to be a row space component, increasing null space component only increases the solution. So in this case, it doesn't make any sense to try to increase it. You have to make it 0. And yep, so 0 is the smallest possible, provides you the smallest possible x. Well, that's kind of like how you can argue it visually. You can argue it analytically too, if you want. All right. So what we have is that the smallest norm solution is a solution x equal to a pseudo-inverse c. So again, the solution to this whole elaborate scheme, let me clear all of this. The solution to this whole elaborate scheme is, as we could have guessed, I think, list is a pseudo-inverse. So if you are asked to find a least norm solution subject to linear constraints, the solution is PINF, pseudo-inverse. It is exactly equivalent to least squares. So what we find is that in terms of solution, this problem is completely equivalent to the problem minimize norm of a x minus c. So those two are completely equivalent somehow, completely equivalent. That is not obvious. We were talking about it last time when we were talking about orthogonality, and I think we kind of, provided enough to be sure that this is the case. But here you can see we just solved two problems independently. We arrived to exact same solution. Okay. Any questions so far?
Z equals 0 only when A is full rank?
A can, in this case, if A is full rank, this problem would have one solution. Yes. So how should I put it? If A is full rank, this part will only have a single solution. It would be, this is what we call domain. We'll talk about it a little bit sooner. And it won't matter what we try to minimize here, because there will be only one x which satisfies this constraint if A is full rank. Okay. So, but in general, you don't have any reason to assume A is full rank. Usually in those cases, it is not full rank. Mm-hmm.
Okay.
Mm-hmm. Yeah, so this is what we talked about. So this becomes the same, like the solution to the problem number 4 is very similar to the solution to the problem number 3. So they are very similar. Okay. Good. Now let us consider problem number 5. Minimize d times x subject to ax equal to b. It looks very similar to the previous one, but now we don't minimize norm of x. We minimize norm of x times some d matrix. Okay. What do we do now? Well, the way to approach this is as follows. we still want to solve this equation. We still want to solve this equation. And we want to solve it to find all possible solutions. So all possible x that satisfies our constraints. We want to find it first. So all possible solutions are again given us a inverse b plus nz. Okay. So still we have the situation where all possible solutions are given as particular solution plus null space solution. Then we can substitute this guy into let's say into here. So we know what x is, and we can substitute it into the cost function. So the cost function then becomes let me use the same color. So it would be, we multiply by d this thing, and we get d times a inverse b plus d times nz. Okay, so this part goes here, and that's what we get. So this is what we want to minimize. This is now what we want to minimize. D times a inverse b plus d nz. Okay. But this we already know. We already know how to solve it. We know that a solution to this problem will be the same as solution to the pseudo inverse. So a solution to the least squares problem, except the minus sign. We will have a minus sign. Again, why do we have a minus sign? Because here, this guy is supposed to be minus if in pseudo is in least squares. Here it is plus, so we will have a minus out front. So we have this minus here. So this problem now gives us the solution. By the way, if we put a minus sign here, we wouldn't have had this issue, and we could put minus sign here, but minus sign will appear somewhere else. This solution, final solution will be the same in both cases. So, all right. So we have our solution, which is, let me clear everything. The solution is pseudo invert this matrix, pseudo invert this matrix, and multiply it by this vector. So this vector with a minus sign that comes from this plus sign here. So this is the solution. Okay, this is how you solve it. But that is in terms of z. Now we want the same solution in terms of x. In terms of x, how is z related to x? Oh, very simple. Z should be substituted into this equation here, and that is how we get x. So x is equal to, well, let me again erase everything and show you how it's done. So x is equal to this part here. Let me maybe be more careful. This part here, right? Plus n, okay, n times the whole solution to the previous equation. So this is the solution to the previous equation. And don't forget the minus sign, of course. Okay, so this is how you assemble the solution. Your particular solution remains the same. Of course, it is. The only thing that you could manipulate in the first place is always your null space solution, never particular solution. So you get your null space solution from minimizing your cost function via least squares. That's what you get. That's what you get. Notice that we have, now that we saw this, let me clear it. Notice we have homogeneous terms. we could bring them out. So if we want, we can bring them out and we get this nice expression in the brackets. Now, more importantly even than those homogeneous terms is the shape of this solution here, the shape of the solution here. So this n times dn, so the inverse times d, that shape should remind you of the formula for pseudo-inverse. And it should even more so it should make you think, what happens if D is identity? What happens if D is identity? What do you mean by identity? Why D should be identity? Well, if D is identity, then this becomes problem 4. Okay, this becomes problem 4, which we already solved. The solution to this problem 4 is pseudo-inverse. So solution to the problem 4 is this guy. This is a solution to the problem 4. So interesting, right? So if D is identity, what we have is n times n pseudo-inverse, which is the same as n transposed, right? So if D is identity, what we have is n times n transposed here. You can say n pseudo-inverse, doesn't matter. And this is a null space projector. Okay, null space projector, null space projector. But this guy here, let me do this. So this guy here is actually a row space vector, because there is a particular solution, because pseudo-inverse is always a row space, it lies entirely in the row space, etc. So this is a row space vector, but we project it into the null space. So what would be the answer? Well, the answer is very simple. The answer would be 0. So if D is identity, this whole thing will be 0. That's what was going to happen. And indeed, we get back to where we came from. Okay. Okay, that is one way to think about it. One way to think about it. Okay. It's one way to think about it. Now, what else can we mention? Well, we could imagine, for example, that null space is identity. So A is a 0 matrix, and its null space is identity. What happens then? If a null space is identity, then what we have here is becomes inf of D, right, times D, right? This is what we get here. So this becomes this. And what is it? What is this pinf of D times D? Well, this is a row space projector. This is a row space projector. Row space projector. Okay. I have some questions about this guy, though. I have some questions about this guy, though, in this case. I have some questions about this guy, though. Why? Well, because if A is 0, what kind of a B should it be? You know, like, how can you find X that satisfies this? Well, the only answer is B is also 0. So particular solution would be 0, I guess. So in this, it's important when you do this to keep in mind, you know, what you're asking for. Actually, I'm not sure if ax equals to b is even defined well when a and b are both zeros. As in, I'm not sure if particular solution makes any sort of sense in this case. Because a row space is trivial. A row space contains only one vector, 0. So particular solution would have to be 0, I guess, in this case. Would have to be 0. So it would be like 0 here, 0 here. Doesn't matter what you multiply it by, it would still be, as answer would still be 0, which is what you would expect. If this guy is identity, so it doesn't impose any restrictions, then the solution to this would be 0, of course.
And it is
Yes.
really possible that the particular solution will be 0.
Is it possible that the particular solution is 0? Is it what you're asking?
Yeah.
Yeah, in this case, if a is 0, and then the only particular solution it can provide is 0, because the row space is trivial.
Yeah, but it's our assumption, like we make our assumption like a is equal to 0 in that case.
Yeah, that's what
Yeah.
I'm specifically just trying to analyze what happens here in two extreme cases. One extreme case is when D is identity. Another extreme case was when A is equal to 0. But the other one, I guess maybe it was too extreme. Maybe it was too extreme.
I
So,
think if
so
D is
basically-
identity, that's good.
Yeah. So there was another one asking.
So basically, Professor, if null space is, null space of A is identity, that means rank of A is 0.
If A is a 0 matrix, the rank is
I
0,
see.
of course.
Yes. That makes sense.
Yep. Good. I hope I didn't derange our like all our conversations with this extreme example. So don't worry, you're not going to see a lot of 0 matrices, but you could, and it's good to be prepared for them. All right. If you don't have more questions, let me move on to something more reasonable. Now, same thing, but we want to minimize now dx plus f. Dx plus f, okay? That's what we want to minimize. Subject to ax equal to b. Okay. So we do the same as before, exactly the same as before. You remember we find all solutions to this equation, and we substitute them here. That is the null space solution. This is a row space solution. We substitute them here, right? And the only difference is that we have f here now. We know how to solve this. The only difference is that we have a constant term here, f. So it would again be, let me now clear, I guess this. It would be again this vector part, right? Multiplied by pseudo-inverse of this matrix here. We would again have a minus sign, which has to do with plus sign here. We substitute all of this back into the original solution, null space solution, same as we did last time, and we get, this whole thing is this whole thing, right? They are the same, and we of course have, as before, particular solution. So particular solution. And null space basis. So the process is mechanical. You don't have a lot of variations here. It's all rather simple, right? Find particular solution, find null space basis, substitute it into the cost function, solve least squares, and get the solution back, right? Substitute back, done, success. So it's easy. That is, by the way, not that, but the previous one, this problem, was the problem that I showed you in the first lecture. And this you can see is kind of like where this best performance was obtained by solving it this way. The only thing that I did in the first lecture was I computed this pseudo inverse and this null space with a single SVD. I did SVD decomposition and used it twice, first to compute n and second to compute pinf. So that's why the performance was so good. I didn't call pinf and null. I called SVD and computed both of them from SVD. So see, lecture 3, you already know the tricks that I was using to get the best performance. Power of algebra. Okay, so far we're still doing algebra, by the way. We didn't go to anything that warrants the name of convex optimization as a separate discipline. Still algebra. Okay, now almost the last one, but now we are very close to something new, very close. So consider this, minimize quadratic function here. So x times h times x plus c times x, subject to, again, ax equals to b, where h is positive definite. Positive definite means its eigenvalues are definite, positive, and it is symmetric. Okay. Positive definiteness we'll study it quite a bit in the course. So but if you want, we can quickly review. Did any of you study already positive definiteness before?
Yes.
Any properties of positive definite matrices that you remember from your studies?
All eigenvalue is positive.
What is the rank of a positive definite matrix?
4 rank.
4 rank, yes. Another property, right? Okay. Maybe you remember eigen decomposition of positive definite matrices, no? But that is, we don't need to use it in this course. But it always have a eigen decomposition, unless I am mistaken or something. But I'm pretty sure always have eigen decomposition without complex numbers. Okay, this one we are not using. Good. So positive definite matrix here, H. One last property that I'm pretty sure you did not study, for some reason no one studies this in algebra, is that you can find a square root of a positive definite matrix. In other words, there is a decomposition H equals to D transpose D always exists for a positive definite H. And you can find such D. D would also be full rank. That just follows. It has to be full rank. It will be also the same shape, right? N by N. So it would have to be full rank. You can try to prove it now that you know how SVD works. You can prove that it is full rank. D would have to be full rank. You can argue somehow that if it wasn't full rank, then H wouldn't be full rank. Okay, so this is a powerful decomposition. In order to actually do it in practice, in something like MATLAB, you probably call something like SQRT M matrix. M stands for matrix. If you are going to do it in Python, there might be something like something also again like SQRT for matrices. So it would have a function that would clearly says that it is SQRT for matrices. Don't try to SQRT a matrix like with a normal square root. Python won't understand what you're trying to do. It has a separate function for that. Okay. Now, so we can always replace H with D times D. That is the whole point of what I was trying to say. Now we can also find such f that 2f times d is equal to c transpose. Where did this come from? Where did this come from? Well, let me before like it is useful, so you would see it in a second. But can we test if it is true? Is it true? Can we always find such f that 2f times d is equal to c transpose? Well, let us find out. Can someone quickly tell me why it is true? If if you already know where I'm going with it.
I think D is 4 rank, so the null space is trivial.
So, exactly. Absolutely right. Absolutely right. D is a 4 rank, so that would be enough to prove that this would always be possible, because we will be able to invert D and prove whatever we want. So let us still try to quickly prove it. So the way we prove it is we just transpose this whole equation. All right, so we have D transposed times F. I mean, we have 2 here, right? Equal to C. Okay, that is the first step. Second step is we just multiply everything by 1/2 D pseudo inverse transposed, right? Or D inverse, sorry, transposed. So F would be equal to inf of D transposed 1/2 times C. And since D is 4 rank, it also means that D transpose is 4 rank. Transpose doesn't change the rank for matrix. So we can always find F by computing inverse of D. That's all. Easy. Okay. Good. No questions about it, right? Or do we have questions? Good. Now, since we were able to do all of this, we can now rewrite our cost function. Our cost function will now be a little bit different. So instead of H, we have D times D. And instead of CX, so let's see, D times D, right? See here, D times D. So instead of C, we have 2F times D. So 2F times D here. Okay, that's what we have. 2F times D. 2F times D. Good. What we can observe now is that this guy is exactly the same as this guy squared. Okay. If we find square of this norm, it will be equal to this guy. I mean, plus F squared, F times F, plus F times F. And the minimum of this norm corresponds to the minimum of this function. I mean, the value of this function, the minimum of this function, would be higher than the value of this one because it doesn't have F squared. But the X at which they get their norms are exactly the same. Exactly the same. So this is kind of like this squared without a constant part. Constant part is again F squared. But constant parts, they don't influence anything in the cost function. You can add them, subtract them. They don't do anything to change X. Okay, we will talk about this later, but we can discuss it in more detail more throughout the course. But this is the whole idea, right? You have this function, which is has a minimum at the exact same X as this function. Okay. So, therefore, this problem becomes exactly the same as this problem, because we minimize the exact same function with the exact same constraints, right? dx plus f, constraints are the same. So we knew how to solve the previous problem, so we know how to solve this problem. The only difference is that we first need to compute d as square root of h, and then we have to compute f as 1/2 d inverse transposed times c. That is it. That's it. Interesting, right? We can solve this problem because we have seen how to solve this problem. Questions about that? Right, no questions. All right. Let me just give you one small comment about what I was talking about with the constant part of a solution. So let's say that what we want to do is to minimize a function like this. We want to minimize function f of x. Okay. It has a minimum somewhere. Let's say we want to minimize a different function, f of x plus 10. You understand that the minimum of the second function necessarily is the same as the minimum of the first function. Why? Well, let's say that we have the second function being something like, I will have to draw, so I apologize, it would look very ugly. Let's say that the function is something like this. Okay, let's say this function is something like this. And the minimum of this function is somewhere, let's say here. This is the minimum of this function. Well, the other, if we shift this function, yeah, it's probably not the best. It looks so ugly. The shifted version of this function here, plus 10, would just be the same, but a little bit higher. But the position of the minimum will stay exactly the same. So the position of the minimum would stay again here. And they will be on top of one another because you just vertically shift the whole function. You don't shift it horizontally. And so the solutions of two functions are exactly the same. If f of x attains at minimum at, let's say, -1, then f of x plus 10 attains at minimum at -1. So this part here is called, what do you call it? Constant part. Why constant? Because it doesn't depend on decision variable. X here, this x, is called a decision variable. We often denote it by saying that, by putting it here under the minimize. So we often denote it like this, under the minimize. So this is called decision variable, x. And, this part that doesn't depend on decision variable, like something like plus whatever expression, which is not going to change if x changes, that is called constant part because it doesn't change. So constant part we can always get rid of because it doesn't influence anything in optimization problems. It doesn't change the minimum of a function. That is the important detail to keep in mind when you deal with minimizations. We have seen it in the previous lecture, actually, when we solved least squares. Questions about it? Okay. Good. Now, finally, I think next slide will give us something that we cannot solve using algebra. Yes, finally. If any of you want, try to solve problem 9. Tell me how we should go around solving this problem. just ideas, you know. Or if you want problem 10, maybe this looks easier. Right? Or problem 11. What stops us from, you know, doing anything here is this inequality. X has to be less than something. X has to be less than something. X has to be less than something. What we mean exactly by X less than B is each element of X has to be smaller than the corresponding element of B. So we can rewrite this as X1 less than B1, X2 less than B2, etc. So this is how you can read this expression here. When we have this expression like this, well, we'll see it soon. We'll see it soon. But it's basically a scaled version of X times, you know, it's still each line of this inequality. This inequality is the same as this inequality represents a vector of inequalities. Each line has to hold independently. Same here. So we don't have any tools in algebra to solve those equations. We just don't. Algebra doesn't provide us tools like that. At least the algebra that we studied in university. So we have to do something about it. And by the way, of course, when I say algebra, of course, I'm oversimplifying. Some algebra books on algebra actually contain algorithms how to solve it. Old Russian textbooks sometimes contain simple X algorithms and stuff like this. But you know, don't be hard on me for trying to be concise. Okay, so this cannot be solved with the algebraic tools, but we can solve it with convex optimization. Convex optimization. So this problem, like specifically this problem here, is called quadratic program. Quadratic program. Okay. So we call it quadratic program. The reason quadratic is because the cost is quadratic. So this component of the cost is quadratic. That's why we say quadratic program. This can be solved with one of a few algorithms. Popular ones are interior point methods, and another one is active set methods. Okay. Two algorithms. You don't have to worry about it. They are implemented. For example, in MATLAB and Python, you can solve them using something like quad prog. This function would solve this problem. You would call it with something like with the variables which would include like H, F, A, B, C, D. That is, I'm still oversimplifying a little bit because quadprog would sometimes assume that you have 1/2 in front of this variable, 1/2 in front of here. Which comes first is depends on the realization. It would sometimes have a lower and upper bounds, etc. But important here is that you can solve this problem. So this problem, you can solve it by calling one function. So same as pinf allows you to call one function to get your least squares solution. This can be solved by calling one function. Okay. And if you think, oh, this is cheating, this is like that's not math, that is cheating territory. Like, sure, there are many functions, but that doesn't mean that we are doing mathematics. Well, you have been happy enough to call least squares so far, right? And the least squares you're not going to compute by hand ever. I mean, maybe sometimes, but I doubt it will be very typical. So when you're going to do a Fourier transform, FFT, you probably heard of those. You're also not going to do it by hand. You're going to call algorithms. So same here, QuadProg, just think of it as one of those quintessential things. Is just something that you don't do by hand, but it can be done, and it is a legit operation. Okay, so something like this you can solve automatically with one call of a function. And but of course, it has to be in this form. In particular, what is important is that here we have linear inequalities. If we don't have linear inequalities, it is just least squares. We can solve it with pinfs and SVDs. So if it has linear inequalities, then it is QuadProg. It can have linear equalities. They are allowed. It shouldn't have any non-linear functions here. So you are not allowed to have a sine of x, etc. Okay. No x squared here. So only linear inequalities and linear equalities. The cost is allowed to be quadratic, but not cubic, not anything else. Can be linear. H can be zero matrix, of course, but that's it. Okay. H also has to be positive definite. Now, in the second part of this lecture, we'll also realize that AX less than B describes what we call a convex region. But that's the second part of the lecture, for which we don't have a lot of time. So we might have to finish the second part of this lecture next time. All right, but that's it. That is what we described here is a quadratic program. Do you have any questions about that?
Can you please tell again, when we use quadratic programming, when we have a linear inequalities?
Yes,
in
when we
constraint.
Yeah, when we have this exact problem, this is a quadratic program. That is when we can use it. We cannot use it for anything else, only for this one. Same as pinf is a solution to specific problem AX equal to B. Quadratic program is a solution to this specific problem. It's just a little bit bigger, but only this one.
Okay, thank you.
No problem. Of course, it is very versatile. So, for example, AX equal to B is part of it, right? You just H equal to identity, F equal to 0, A and B are equal to 0, C equals to, whatever your, here we have like this linguistical thing. This part is your, let's say, least squares. If you want to solve least squares with QP, you can, right? This is your least squares. Here you put identity. Let me put it like this. Here you do identity. Here you this part you go put it to 0. This to 0, and that is your least squares. We show that it is equivalent in the problem number 4.
9, I think 9.
No, number 4.
Okay.
Let me show you. Here, we show that this has the same solution as this.
Yeah. Okay.
So QP is very versatile. All of those are QPs. This is a QP. This is a QP. This is a QP. Why? Because this cost function, if you square it, it would we have to be careful here, of course, but unless I'm mistaken, if you square it, you are not going to shift the minimum of this function. So yeah, I think that is correct. So if you square it, the minimum of this function is not going to shift, and that is how you can but I'm not 100% sure here. So don't take. Let's not be like too rush. Those might not be QPs because of this. But if we had here squares, so let me cheat. Not 3 squares. Okay, so if we had squares here, then it would all be QPs, and we could solve all of them with quadratic programming. Since they're not QPs, you have to actually prove that you can like transform them into QPs equivalently. Soon enough, I will show you how to solve problems 9, 10, 11 without transforming them into QPs. But all right, more questions. More questions. Okay, now we have still, I think, about 15 minutes at least, unless I'm mistaken. How much time do we have? Can you tell me?
Almost, I think, 45 minutes.
45? 35 minutes?
No, 35. 35.
35?
Yeah.
Great. Then we'll probably have enough time to finish. So let me go to the second part of this lecture. That is domain and convexity. We'll finally understand why convex optimization comes up so often. What's this word? Has it to do with anything? All right, so let us first start by solving some very simple problems. So can someone solve for me the problem number 1? Someone solve me the problem number 1. Find the minimum of a function x squared plus 2.
0, 0.
Exactly. 0, 0. You can you tell me how you solved it? I mean, other than intuition. Intuition, of course, is sufficient here, but
F is have all positive value.
Yes,
so
absolutely. Yep, you can say it that way. You can also just say at the optimal point, derivative of f is equal to 0. So derivative of f would be with respect to x is 2x. With respect to y is 4y. Set it to 0. X equal to 0, y equal to 0. So that is another way through derivatives. Okay. Now find me problem 2. Same function, but x would be like this, y would be like this. Someone solve me the problem, please.
One and two.
1 and 2. Let's find out. Somewhere here is written solutions. So here, exactly. exactly. Great. So how did you solve it?
Generally speaking, we have squares, so x square, minimum of x square is minimum of x, and for y, same thing. So just select the minimum of ranges of x and y.
Good. Exactly. Sounds very good. Another way to do it is to say functions attain minimum at when the derivative of the function is equal to 0, or at the edges of the domain. And that is when maybe you remember high school terminology or first year of university terminology, domain. So those are the edges of the domain. So you have to check which one is smallest, like 0, 0. It's not even in the domain, so you can't use it. 1, 2, maybe that is the smallest, and indeed this. Of course, you have to be careful here because the edge of the domain is not actually just 1 and 2. It is actually a whole square. So you have to check all the edges on the square. So it's we are cheating here a little bit. But yeah, your solution is exactly correct. Your solution is exactly correct. We have 25 minutes. We had 25 minutes. Great, good. Thank you. Thank you, Sama. So this should tell you something. The function stayed the same, but where the function is defined changed, and that changed the solution to the equation. So somehow it is important to know the range of variables. Important observation. So we call this space of all allowed values of the decision variables domain of optimization problem. So domain of optimization problem is the range of all allowed values of decision variables. Decision variables in this case is x and y. And the domain in this case is between 1 and 2, between 2 and 5. Okay, so this is what domain is. That's what domain is. Now let's just solve a little bit more problems. Someone please find me the solution to the problem number 3, minimum of a function minus x squared on this domain. Go right ahead. It's not such a crazy problem.
I think minus 3.
Minus 3 and 0. We have two options, right?
Minus 3, I guess.
Okay. So alternatives, minus 3?
Yes, minus 3.
No one wants to argue. Someone said 0, so.
I say 0 because if we just draw this function, it will be something like paraboloid that looks with his branches down. So yes. The highest maybe, but it's okay. I'm incorrect. So
okay.
Yeah.
No, good. For maximum you would have been correct. That's fine. Solution is minus x equals to minus 3. Great. Exactly. So the logic is kind of the same as before, right? I think you just use your intuition about how it goes, etc. So good. Now, can you please solve me problem number 4? Minimum of a function minus x squared. X is allowed to be any real number.
Maybe minus infinity?
Minus infinity.
Minus infinity, you say. Okay. What about plus infinity?
Yeah, it's also same. So minus infinity to plus infinity.
Okay. Infinity is not number. So when I ask for a solution, unfortunately, I cannot accept the answer infinity. It is, reasonable enough. I don't disagree, but it's kind of like when we talk about computer implementations, infinity is almost the same as not a number, right? So it's kind of like it's not really an answer. Let's see what the slide says. What is the answer to the slide? Yeah, the slide says the problem has no solution. And it is true. The problem has no solution. The problem has no solution. Why? Why doesn't the problem have a solution? Because it is unbounded. So we can always go down into towards infinity. Now here, I think we need to bring some conventions in, because you will tell me that no, the problem has a solution. Infinity is a solution. Minus infinity is a solution. And I would have to argue somehow that this is not correct. And for that, we need rules of the game. So let me give you some idea of how we can discuss this. You don't have to agree with me, by the way. It's just I'm just giving you like conventions. It's not something you have to like subscribe to, but you will probably appreciate the usefulness of what I'm going to talk about. So solution is something that you can so let's say x let's say x solution is I wonder how we should write it. Maybe in a graphical way it would be actually better. Well, what I'm trying to say is it is a limit of a sequence, right? So it is a limit of a sequence of x as that makes the function approach its minimum. That makes the function approach its minimum. So let me, I guess, just try to show it first graphically. Graphically, maybe it would be better. So let's say we have x. Let's say let me even show you like the function. It's the function looks like this. It grows with those lines. I don't know if what I draw makes a whole lot of sense, but what I'm trying to show here is that the function is kind of like increases, right? It's like a paraboloid, let's say. What is the solution to this function, to this problem? Well, we have a sequence of x, which somehow approach this minimum of the function. They approach it. And eventually the sequence the sequence converges, okay? The sequence converges. So the distance between the neighboring x's goes towards 0, okay? And the functions, like the sequence of values of the function that this represents also stops dwindling, okay? So you have a converging sequence of x. I guess that's, I think that's a language that we can use effectively here. You have a convergent sequence of x. The sequence, the f of x on the sequence stops changing at the end. So as the sequence goes towards infinity, the f, neighboring f are no longer decreasing. They are like staying almost the same. They decrease, but they decrease small and small and small. Okay. And x, the distance between neighboring x, is also becomes less and less and less and goes towards 0. So the limit of this sequence is a solution. Okay, the limit of the sequence is a solution. For example, let me draw something realistic. So we have a number line, and on this number line we consider interval. Consider interval. Let me do it this way. This interval. Okay, that is what we are interested in, and we want to find the minimum of a function that is given like this. So this function, we want to find its minimum on this interval. Here is how it goes. So you can instantly see that the solution should be somewhere here. That should be a solution, because this is like where the function is smallest. But how can we argue that this is a solution? Well, we can say, starting from somewhere, we can draw a sequence of x, right? Which would go towards the solution. And then when they, are stuck against the solution, they stop changing. So all subsequent x remain here, okay? And the corresponding values of the function are this, right? They decrease, they decrease, they decrease. And then when they stopped here, they stop, they decrease less and less and less, or they stop decreasing altogether. They never increase, though. That is, of course, important. If you're going to get as a sequence, this will be a sequence of decreasing solutions. All right. So solution provides us this limit to a sequence of x, which provides a decreasing sequence of values of f. And the limit of the sequence is the solution. Now, if we don't have limits, if we can go down towards infinity, x is never going to converge to anything. It just goes like minus 1,000, minus 2,000, minus 3,000. It goes without any change. The sequence doesn't converge to anything. And the function is never convergent to anything. It just goes down and down and down. So you don't have the idea of convergence here. And that is a problem. You don't know where to stop. Of course, analytically speaking, you can say it's never stops. It's going towards infinity. And that's fine. I mean, limits can have infinity as a result. But we want to operate with numbers. So solution to the equation is the limit of a sequence. That is, that is quite what we like. The limit of a sequence is the solution. Okay. Fair enough. Fair enough. I hope this somehow gives you an idea why problem 4 would say it has no solution. Since we like to think of solutions as the limits of the sequence, and since we like them to be numbers. Okay. That does mean that in a different discipline, you couldn't say that this has a solution. Only in convex optimization, we say it has no solution. Good. Questions about it? We can go back. Okay. Problem 5. Can someone solve me problem number 5?
Also no solution.
No solution, yes. So you can see that the problem number 4 wasn't solvable because it didn't have a bound. It didn't have a domain. Domain was too big. Problem number 5 is again not solvable because the domain is too big. Even though it has a domain is like limited, still too big though. So we can call those problems unbounded problems. Okay.
May I have a question?
Yes.
So the boundary is too big, means even if we have lower bound as minus 1,000, still considered unbounded, or just because it's in minus infinity?
No. It's a good question. I think it is addressed somewhere in the next slide, I think. But the idea is the size of the number doesn't matter. Can be minus a billion, anything, doesn't matter at all. The solvers will have problems with big numbers, that's true. But, for us, it doesn't matter. We can always get around big numbers. The reason why we say it is unbound is because the solution, we cannot define it, right? We don't have a sequence which converges to something. We want the solution to be like a limit of a sequence. Okay, and when we go towards infinity, we just march, we don't converge to anything. That is the kind of like the intuition behind it. All right.
Okay, thank you.
Now, I think, your question will be addressed somewhere in the slides. So let's just try. Problem number 6. Can someone tell me something about it? What is the solution? Number 6.
1.9.
We have 0 and 1.95.
Sorry, I didn't attempt the maximum.
1.99.
Yeah, 0 is not a solution because 0 is not in the domain. 1.9, yes, one of you said. 1.9 or 1.99?
99 bar. 1.99 bar.
99 bar. So what is 99 bar? What kind of a number is 9 bar?
It's
that
like
means-
repeating 9 after the point.
Yeah, I know what kind of like this means linguistically. It means that I need to keep pressing
Yeah.
9. But how long do I press? When do I stop?
There's no limit.
Yeah, but this is a problem because I want to output a number. I have to stop somewhere. Okay, I have to stop somewhere, and this is
Yes.
not a solution. Why this is not solution? Because this number is still closer to the solution. You understand, right? Like we have a problem.
Understood.
We have a problem because this number, adding something else here, it still gets us closer to the solution. So somehow this is not a solution. What this thing that I just draw, sorry for the mess, is not a solution. I have to keep pressing 9. Okay. So this is not a solution. In fact, let me erase this. In fact, what you want me to do is something like this. In our notation, I think we usually call it you like bar notation. I think we usually write something like this, where we say in brackets means infinite repetition, but we can go with bar if you want. Fine with me. Something like this, right? So this is actually has a number. This is not a irrational, like a number that we cannot express. No, this has exact value that we can express, and it is equal to 2. 1.9 bar is equal to 2. Does this surprise anyone?
You are right. Yes.
Is there anyone who wants to challenge this? 0.9999 repeated is equal to 1, for example.
Actually, there was some proof. Actually, some mathematician proved that it is equal to 1. I saw.
Yeah,
that.
of course. No, it's it's part of standard calculus textbooks, at least the ones that I read. But not everyone reads those chapters. Like, you only have so many months to complete calculus. So is there someone in the class who doubts this? Just want to make sure that we don't look as if we are doing magic. So what we do here, this is called basically in calculus, this is treated as defining numbers. So you could try to define a calculus where those two numbers will be different numbers. You could try. But standard way the calculus is defined, those are the same number. Because the difference between them is just this 0.000, and 0 goes all the way, and it never stops being anything but 0. And you can like try to prove it using some axioms, etc. For us, though, for people who are going to use computers, the thing is that we don't have any precision, machine precision, which would allow us to find the difference between 2 and 1.9999999, right? Because no matter which precision we use, it will always be 0, because it is the number of zeros in this in the difference between 1.99999 and 2 is infinite, right? It never stops. It's always going to be 0, no matter which machine precision we use. So, you have two options. First, get a calculus textbook and find the proof that those two are the same numbers, or you can just think that for the computers are the same numbers. The result is the same. All right, but I suggest doubt everything, including what I just said. So double check for yourself. So those are the same numbers, but that means that the solution that you provided me is not in the domain. Please notice, this is not in the domain. X has to be less than 2, not equal to 2. Okay. So x is not 2 is not in the domain. So you cannot tell me that 1.9999 is a solution. You understand it? Another way to say it would be that the sequence of x, like when we try to construct sequence of x, which should converge towards the solution, converges to the value outside of the domain. Okay, so there is indeed a convergent sequence of solutions x as it approaches 2 from the left. It converges, but converges to a number that is outside the domain, and that is a problem. And in convex optimization, we solve it very easily. We don't allow strict inequalities. So we would see later, but those type of inequalities are not allowed. So we're not allowing strict inequalities. It should always be non-strict. Should always be non-strict. Because otherwise we would have a situation where the solution lies on the boundary and we will converge to the solution which is outside the boundary. So problem 6 doesn't have a solution. Problem 6 doesn't have a solution because of the strict inequality. Let me just double check that what is written here is what I said. Yeah, has no solution. But that is because we abused the way we, abused the problem. We asked for strict inequality. Let's do problem 7 and then we'll continue discussion. Can someone tell me about problem 7? Minimum of the function x2. 1, exactly 1. So just because we have this strict inequality doesn't mean that we don't have a solution. This strict inequality, same as the complete lack of boundaries, would only cause us problems if the solution goes this way. Okay. So this has a solution, 1. This doesn't have a solution. In fact, it is kind of stupid to try to solve problem 6 in engineering sense. In mathematical sense, it is completely fine. In engineering sense, it is kind of stupid. Why? Let's say you are trying to find the solution in order to compute some parameter somewhere. Okay. And 1.99999 is acceptable value for you. Okay, because you say as long as it is less than 2, acceptable. So 1.99999 is acceptable, but 2 is not acceptable. 1.9999999 is acceptable. 2 is not acceptable. Somehow, this problem statement says that there is an infinitely small difference between acceptable and non-acceptable values. Doesn't happen in engineering. You will never be able to formulate a problem where there is an infinitely precise difference between acceptable and not acceptable values. There is always a margin. There is always a margin. So if 2 is unacceptable, then 1.9999999 is also unacceptable. For engineering reasons, it means that the height, breadth, it's difficult to pronounce, difference between error and being acceptable. So in practice, if you want to solve this, instead what you will solve is something like this: x less than 1.99. Sorry, I was trying to type and I didn't type. You will solve something like this: x less than 1.99. This will be engineering way to solve the problem, and of course it will be strict inequality, non-strict inequality. So this is how we would write it in engineering context. We would identify the margin that we are willing to observe, and we write a non-strict inequality with the margin built in. So this problem we cannot solve. Problem 6 we cannot solve, and we don't want to solve it. It's a bad problem. Okay. So, all right. I think we are out of time, right? Unless I'm mistaken. Is this true, or am I being too fast?
Yeah, we are out of time.
Yeah, we're out of time. All right. So next time we'll finish this material, and we will start a new lecture. I think it is all right. We are not falling behind. I'm trying to kind of like speed up as lectures, so that's why the material is a little bit, it always feels like we have too much. It's okay. We are going faster than all previous years, so it's okay. Don't worry. We can take more time for any of this. If we have any questions about the material so far, about the lecture,
I have one actually.
Go.
Can we, for example, take the closest natural number to the upper bound? In this case, number 1, let's say, to solve the problem, or
rational or integer?
Natural number, like 1, 2, 3, 4.
Integer.
Case we can take number 1 as the closest to the upper boundary.
Integer, closest integer, right?
Yes, integer, exactly.
If we can, but if we are restricted to integers, but let's say we are not restricted to integers. In engineering problems, we usually are not restricted to integers.
Okay.
In fact, there are a class of problems when we are only using integers, but that is when usually we want to pick something. Like, let's say we want to pick, 1 house, 2 houses, 3 houses, something like this. That's economic style problem. In robotics, it will be like we want to pick, let's say, connect 1 battery, 2 batteries. That's artificial. Usually, a typical example of integers is we want to pick road number 1, road number 2. And that is a typical example when we path plan. We say go left or go right. Left is 1, right is 2. Pick 1. That is when we pick integers. But when we want to optimize something, like let's say weight, mass, input, control output, anything, we usually don't restrict ourselves to any sort of coarse precision.
Okay.
No, thank you for the question. All right, more questions? Okay. Good. With that, we'll finish the lecture. Sorry for if I took too much time today. Next time we'll finish this material and we'll go to the next lecture. So see each other on Thursday. Okay. See you then.
Okay, sir. See you.
Yeah, bye-bye.
Goodbye, Professor.
Bye, Chris.